Hello everyone, welcome to my YouTube channel. So today I am going to discuss an interesting real analysis problem. Also, you can say an interesting metric space problem. Okay, so we know that continuous image of closed bounded set is closed bounded. In particular, continuous image of a compact set is compact, and any compact set is bounded, right? Now my question is, if any continuous function from A to R is bounded, then is A compact? Okay. So first I will discuss this question taking A as a subset of real number so that you can understand easily, and then I will generalize this to a metric space. Okay, so solution. Let A is a subset of R. Okay, since A is a subset of R, if we want to show A to be compact, then it is enough to show A is closed and bounded. Okay, so my first claim is A is bounded. If not, if A is unbounded, consider the function fx equal to x from A to R. Since fx equal to x, since A is unbounded, then definitely f is also unbounded, which contradict our given condition that any continuous function from A to R is bounded, because we know that fx equal to x is always a continuous function. Now my second claim is A definitely closed. If A is not closed, then there exists P belongs to R such that P is not in A and P is a limit point of A. It is definition of a closed set, right? If a set is closed, that means that set must contain all of its limit points. Now, since I am assuming that A is not closed, that means there exists a limit point of A which is not inside of A. Now consider fx equal to 1 by mod x minus p. Now f is definitely a continuous function. Why? Since mod x minus p is always not equal to 0. So definitely f is continuous. Now since p is a limit point of A, we can always find a sequence xn inside A such that xn converges to p. Now if xn converges to p, then f of xn definitely unbounded, because here in denominator xn converges to p, that means xn minus p, modulus of xn minus p tends to 0 as n tends to infinity, and that will imply f of xn is unbounded. Hence we are done. So first we are assuming A is a subset of R, then we show that A is closed and bounded, because if A is unbounded, then it is enough to consider fx equal to x, I mean identity function on A, and if A is not closed, then there exists a limit point of A which is not inside A, and then we consider fx to be the function 1 by modulus of x minus p. Okay, so that's why in this way we can easily show that A must be compact. So in real line case, A must be closed and bounded, but it is quite difficult to prove in generalized metric space, because we know that in arbitrary metric space, closed and boundness does not imply compactness. If X is compact, then definitely it is closed and bounded, that is okay, but converse is not true. So in that case we have to use some extra theorem. So let's generalize it. So consider XD be a metric space. Okay, so now I assuming A to be X. Okay, so don't be confused, this is now X just, since we are generalize this in a metric space. So X to be a metric space. If XD is not compact, then XD is not sequentially compact, because we know that compactness and sequentially compactness is basically equivalent condition in case of metric space. So if XD is not compact, then XD is not sequentially compact. Then by definition of sequential compactness, xn be a sequence. We have always a sequence xn such that xn does not have any convergent subsequence. Okay. Now consider a subset A, which is basically the sequence xn. Then definitely A is closed because A does not have any subsequence. Since A does not have any subsequence, A does not have any limit point. So since A does not have any kind of limit point, so that's why A definitely closed. Now we are going to use a interesting theorem, that is Tietz extension theorem. If you don't know, I think if anyone read metric space very well, compactness very well, then he or she should read Tietz extension theorem, Modichon lemma. This is because this is very important. Also, if you read topological space, I mean topology, then you should read this for normal space. But I just want to tell that it is very important theorem. If you don't know this theorem, then please read this theorem from any standard book because this is available. Okay. So the theorem says that if A be any closed subset of a metric space X such that f is a continuous function from A to R, then we can extend this map to the whole space continuously. Okay, so what it says that if A is a closed subset of a metric space X, and if I have a continuous map from A to R, then we can extend this map to X to R. Okay, this map continuously. Now we already have a subset of X which is closed. Now we are going to use Tietz extension theorem on this set. Now I define A to R is basically f of xn equal to n. Okay, that means f of x1 equal to 1, f of x2 equal to 2, f of xn equal to n. Definitely f is continuous. Why? Because we know that in case of metric space, inverse image of any closed set is closed. This implies f is continuous. Okay. Now consider any subset of R which is closed. An inverse image is inside A. If inverse image of that set is finite, then definitely that is closed because any finite subset of a metric space is always closed because in general it is compact. And if it is infinite, if inverse image of a closed subset of R is infinite in this case, then also it is closed because A itself is a closed set, and that's why A does not have any kind of convergent subsequence. Then if inverse image of some closed set is not closed, then we will have a convergent subsequence because that will imply that the subset of A must have a limit point, and that will imply A must have a limit point. But we already assume that A is closed, and A does not have any convergent subsequence. So that's why F is definitely continuous. It is obvious. And now by Tietz extension theorem we can extend this map. So we can extend this map F tilde, and that is extension from X to R. And this is also a continuous map because we continuously extend this map. Now observe that f of xn equal to n for all n, that will imply that f is unbounded. And since we are going to extend this map on whole space, then definitely f tilde is also unbounded because f tilde and f agrees on the subset A of x. So f tilde is also unbounded. But it is given that any continuous function from A to R, in general I am assuming that any continuous function from x to R is bounded. But here we got a continuous function f tilde which is unbounded. That is a contradiction. Hence, our assumption is wrong when XD is compact. Okay. So this is the important thing. Here we are using a strong result, that is Tietz extension theorem, and that is very important. And this theorem is very helpful to prove other nice interesting results. Okay. So this question actually a subjective problem of ISI.